Hello everyone, my name is Zhao Yandu and I come from the University of Electrical Communications. My topic is on-device federated learning with fuzzy logic-based client selection. Here's the outline. My presentation has 4 chapters. Chapter 1, I will give a brief introduction of the background of federated learning. Chapter 2 introduces the fuzzy logic-based client selection scheme and the architecture of on-device federated learning system. Chapter 3, we use Raspberry Pi and laptops to evaluate the proposed scheme in terms of its effect on federated learning by comparing with existing baselines. Chapter 4 is the conclusion. With the rapid development of artificial intelligence technology driven by big data, machine learning techniques are widely used in real life. Although deep learning technology has developed rapidly, the existing technology is still dominated by a centralized architecture centered on a cloud computing platform, in which data is centrally stored and processed. In addition to high latency and computational overhead, centralized architecture also has data privacy and security issues. If the privacy issues are not fully considered and resolved, there will be risks of sensitive data leakage and network attacks. Machine learning algorithms require a large amount of training data, while actual data is required to be stored in different organizations due to industry competition, privacy, and security restrictions, and there are considerable obstacles to data integration. Federated learning is a new distributed machine learning paradigm that can secure user data while leveraging device local data. Federated learning enables a large number of devices to collaboratively train machine learning models while protecting user privacy and enabling participants to benefit from each other. The left side of this figure shows the federated learning scenario at the Internet of Vehicles environment. Purple and blue vehicles in the picture are smart vehicles, and they participate in the entire federated learning process together, with pedestrians carrying smart devices as clients. First, each client downloads the latest model from the server. Then, each client uses the local data to train the model and upload the encrypted gradient to the server. And the server aggregates the gradients of each user to update the model parameters. Finally, the server returns the uploaded model to each client. Most of the existing research on algorithms and privacy protection in federated learning is based on this scenario, and the performance of the proposed method is verified through simulation experiments. However, the consideration of the client in simulations is often insufficient, and the IoT devices usually face problems such as limited computing resources and poor available bandwidth. Therefore, building a test scenario composed of real devices is necessary, as shown in the right side of the figure. We propose a federated learning architecture using a laptop as a server and the Raspberry Pi as clients. The ease of development of the Raspberry Pi allows it to emulate a wide variety of devices. Parameters that affect the performance of federated learning, such as the data size of each client and the available throughput, can be set independently to achieve reliable verification of the proposed method. Motivation of our study are introduced here. First, evaluating the time to run federated learning on each client in the simulation is difficult. We have published our previous research in IEEE Open Journal of the Computer Society, and we find the limitation that the simulation has. Thus, we want to verify the performance of the proposed client selection method for federated learning in a realistic network. Moreover, we want to find parameters affecting federated learning performance that cannot be detected by simulation. Federated learning networks consist of a single server and several vehicles as clients. The server selects parts of clients from thousands of participants to train the model over their local data because of the limitation of communication resources. Consider limited computing and communication resources. It is important to select appropriate clients from a huge number of users to participate in the training process. In vehicular networks, the problem of choosing proper clients is particularly complex due to the heterogeneity of network users. In order to achieve an efficient client selection in federated learning, some key factors should be considered as input variables, including the quantity of samples on the client, available throughput, and the computational capability of each client. The sample quantity, which means training more data in one communication round of federated learning, could lead to better accuracy. The storage space limits the amount of data stored by an IoT device, and the amount of data or data characteristics contained in different IoT devices often differ greatly. Therefore, choosing devices with more data could be of great help in improving federated learning performance. We divided the sample quantity of each IoT device into 3 levels: sufficient, average, and shortage. The next factor is computational capability. The task processing capability of IoT devices varies greatly. We define 3 linguistic variables of computational capability to represent the idle computing power of each client: strong, middle, and weak. The final factor is throughput available. The communication capability of IoT devices are also different. Although some devices have strong communication capabilities, other tasks may need to be performed when a federated learning task is required. Therefore, selecting clients based on the currently available throughput can shorten the federated learning time, thereby improving the overall efficiency. We divided the throughput available of each IoT devices also into 3 levels: good, middle, and poor. The next is the output from fuzzy logic. We use fuzzy logic to comprehensively consider the above 3 IoT device features that could greatly impact federated learning performance. The evaluation result of each candidate of federated learning client is mapped to 6 levels. The higher the level of the candidate of IoT devices, the higher the priority of the device should be selected as a federated learning client, and selecting this device could improve the performance of federated learning. The proposed client selection method based on fuzzy logic includes 4 steps: fuzzification, fuzzy rules, defuzzification, and client selection. Fuzzification is the process that transforms the crisp input value into a linguistic variable. Then we use Mandelin fuzzy inference method to synthesize the 3 factors introduced above. To fuzzify the output value, we define 6 different levels for rank from 0 to 5. Then 3 input variables are associated with the output variable after applying fuzzy rules as shown in this table. There are 27 fuzzy rules because each input variable has 3 linguistic variables. Each candidate client of federated learning will obtain a fuzzy logic score according to its state. The higher the score, the better the federated learning performance could be obtained by the chosen device. Finally, the server will select the most suitable client for federated learning according to the scores of each device. This chapter will introduce the on-device federated learning system with the fuzzy logic-based client selection method adopted. The experiment setup and the evaluation results will be presented in detail. We use 6 Raspberry Pi and 2 laptops as candidate clients. Using the German traffic sign recognition benchmark dataset in order to simulate a vehicular network. In this paper, we assume the scenario that the federated learning server would choose 2 devices as clients among the above 8 candidates. We evaluate accuracy and the processing time, including computation time and communication time, when running federated learning on real IoT devices Raspberry Pi to provide a benchmark and the real-world IoT settings. To verify the effectiveness of the proposed scheme, we choose 4 baselines for comparison: the greedy for sample quantity, greedy for throughput available, and the greedy for computational capability. This method only considers a specific characteristic of all candidate devices, which is not fair when choosing clients. The random selection method selects different clients each time, resulting in very different experimental results. The results presented in this paper for random selection is the average of all results after 10 federated learning process runs. All these experiments run 3 communication rounds. In this section, we assume that the data stored in the device follows the IAD method, and the difference in the SQ factor represents the amount of data in the device. Sufficient indicates that about 39,000 training images stores in the client. Average indicates that about 20,000 training images stores in the client. And the shortage indicates that about 8,000 training images stores in the client. Although the amount of data stored in the client varies, 43 classes of data are held in each client, as shown in the left side figure. The federated learning processing time of 4 baseline and the proposed method are compared. The blue bar in this figure represents the time and the device takes to process the federated learning task, namely the time spent on model iterations on all clients. Greedy CC method has the lowest computational time because the server could select the 2 devices with the most abundant computing resources as the clients to obtain the shortest computational time. However, the greedy CC method does not consider other factors of the device. The available bandwidth of the client 2 is very poor, so the communication time spent in this method, namely the time for transferring the model between the client and the server, is very large. The communication failures often occur. Like the greedy CC method, the other 3 baseline methods only consider a single factor or select clients randomly. On the other hand, the proposed method comprehensively evaluates the currently available bandwidth of the device, the number of samples, and the task processing capability based on fuzzy logic. Therefore, the server can select more appropriate clients for federated learning. The proposed method can not only complete the federated learning task quickly, but also make communication between the server and the client more stable. Accuracy comparison of the proposed method and the 4 benchmark method after 3 rounds of federated learning is shown on the right side of this figure. The proposed method could achieve the best accuracy in each round of federated learning. Selecting clients based on the only one factor does not benefit the overall federated learning architecture. Focusing only on the computing power of the device could cause communication problems between the server and the client. Focusing only on communication capabilities will degrade accuracy. The proposed client selection method evaluates each candidate device based on fuzzy logic. The server and the clients selected by the proposed method can build a more stable federated learning architectures and obtain the best accuracy. In the previous section, we evaluate federated learning in the scenario where the device holds ID data. However, in realistic scenarios, each IoT device often has different kinds of data. Therefore, we evaluate federated learning in the scenario where the device holds non-ID data. In this section, sufficient The samples quantity indicates that about 40 classes, 36,000 training images stores in the client. Average indicates that about 30 classes, 20,000 training images stores in the client. And shortage indicates that about 20 classes, 8,000 training messages stores in the client. As shown in this figure, we could notice that the accuracy of each client selection method in the non-ID scenario has decreased. Non-ID data could greatly impact the accuracy of fed average algorithms or other similar algorithms, since the distribution of the dataset on each IoT device is very different from the global distribution. The local objectives of each client are inconsistent with the global optimum. The above experimental results show that the federated learning architecture composed of the server and the client selected by the proposed method is more stable, and the federated learning performance is better than other baseline methods. In this paper, we propose an on-device federated learning architecture with modified fuzzy logic-based client selection scheme. We consider three input variables of IoT devices in the proposed scheme, namely the number of samples, computational capability, and available throughput. In order to verify the effectiveness of the proposed method, we use Raspberry Pi and laptops to build a real federated learning environment. Moreover, both the ID dataset and the non-ID dataset are considered during experiments. Experiment results show that the federated learning server could choose the appropriate clients to get the best performance through the proposed client selection scheme. Thank you very much for your attention.